Towards the end of the last class, we had realized that there are three basic operations which occur in symmetry elements. One is an operation about a point, the other is an operation about an axis in a certain direction that will introduce different kinds of axes that are possible. In general, there are n-fold axes which can exist, that is n equals 1 to infinity. The infinity axis can be considered as the one which generates a sphere, which is the ultimate most symmetric object. So, the number of rotations axes that are possible are quite large in number. On the other hand, the operation about a point is restricted, and also the operation about a perpendicular to a plane is also restricted. It depends upon where we put the plane. So, when we consider the crystalline state, this becomes extremely important in the sense that the crystals have this particular property, that is the property of periodicity. So, since we have this periodicity as a main issue in crystalline material, the periodicity introduces certain restrictions. The restrictions come basically on the rotation axis, because the point is unique, the reflection across a plane is also unique given the direction, whereas given the direction, the axis of symmetry can be very different from each other. It could be a two-fold axis where 180 rotation is there, a three-fold axis where 120-degree rotation is there, which we saw actually with examples taken from Escher's diagrams. So, the Escher's diagrams were kind of indicative that we can have these rotation axes possible in a two-dimensional lattice. We were examining only a two-dimensional lattice. What we will now do is to see why this now becomes only 5 possible rotation axes in case of crystalline objects. It becomes only 5 possible rotation axes, the rotation axis being 1, of course full rotation 360 degrees, 2, 3, 4 and 6, that will be corresponding to 180 degrees, then 120 degrees, 90 degrees and 60 degrees respectively, and no other axis is possible. We shall examine why it is so, and this is a very big advantage when we look into crystalline objects. In fact, this restricts the possible number of symmetry positions we can have in a crystalline object, and the whole issue rotates around the concept of periodicity. So, the periodic repetition of objects, or for that matter the periodicity that is associated with the three-dimensional space, decides what kind of rotation axis we can have for a given system. Let us examine this with a one-dimensional lattice. The one-dimensional lattice is shown here in terms of the red dots, and then the possibility of creating a two-dimensional lattice is through the rotation either about A or a rotation about B. The rotation angle can be defined as delta, and delta can be any value in principle. So, we can now generate the lattice, but the lattice should have the periodicity imbibed in it. That means the distance between A and B should be at a distance t, which should be the same distance to the next point and so on. And after rotation, the point which we generate should also obey the laws of periodicity. That means the two-dimensional positions of A prime and B prime which we are going to generate, A prime being generated by rotation axis operating on B and taking A with an n-fold rotation. The n-fold rotation can be defined as 2 pi divided by delta, where delta is the angle of rotation, 2 pi being 360 of course. So, if we now sit at B and look at A and start generating the lattice points, which eventually occur because of the two-dimensional periodicity in the lattice, then we can generate n such lattice points. The n minus 1th lattice point will be A prime, one lattice point which is just before generating again the point A. A similar situation can be imagined when we sit at A and start at point B and take the point B around, and the point B when it goes to the first position will be B prime, and so on in the n possible rotation axis. So, effectively we therefore generate the two-dimensional lattice, the condition being that the object or the red dot which represents the object should be repeated at periodicity associated with it being t. So, by definition therefore, B A prime will be also t, the translational periodicity. So, also A B prime, which is translational periodicity. So, if we now calculate the distance between A prime and B prime, the A prime B prime will be a multiple of t, because by definition of a periodic lattice it has to be a multiple of t. It could be 1 times t, 2 times t, 3 times t, but that value of m is an integer. It is only an integral multiple of t. In that situation we define a 2-dimensional lattice. And therefore, the definition of a 2-dimensional lattice comes into the picture here, and the presence of the 2-dimensional lattice puts a restriction on how we can get the value of delta organized. Let us examine it now from a simple arithmetic point of view or a trigonometric point of view. So, let us take this distance A prime B. A prime B, as by definition, is A B, because now we said that this is the n minus 1th lattice point. So, one point before the nth point, which happens to be B, and therefore we have A B prime and therefore it is equal to A B, and that is t, and the angle which is B A angle B A B prime. So, this should be this angle which is referred to, the angle A B A prime, which I should be referring to here. The angle A B A prime will be equal to 2 pi divided by n, because n is the fold of rotation. So, if n is equal to 1, it is 360 degrees, if n is equal to 2, it is 180 degrees, and so on. So, B A B prime is 2 pi divided by n, so also A B A prime, and both of them define our delta value. Now, the question is that these two values remain t, and B prime A prime defines mt, but what we can do by geometry is we can write B prime A prime as equal to A B, which is the translational periodicity, minus A B prime cosine delta, A B prime cosine delta, and B A prime cosine delta. So, this expression for B prime A prime will ensure that we have now B prime A prime, which now can be written in terms of t. So, A B is t, A B prime is t, A prime B is t, and therefore, this is be 2 times 1 minus 2 cosine delta. So, 1 minus 2 cosine delta times t defines B prime A prime, and by the laws of periodicity this should be a multiple of t, which happens to be the translational periodicity. Therefore, we can write an expression mt is equal to t times 1 minus 2 cosine delta. So, this would give us the value of cosine delta as 1 minus m divided by 2. We all know the property of a cosine function, and the cosine function will now be an oscillatory function, and the values corresponding to 1 minus m divided by 2 therefore, is a restricted value. The restrictions which come on m will be between minus 2 and plus 2. So, m cannot take any other value other than these minus 2, minus 1, 0, 1 and 2, representing different types of rotation axis. For example, in this table we have given the value of 1 minus m is equal to minus of 2, which corresponds to a cosine delta of minus 1, and cosine delta of minus 1 is the value pi, which is 180 degrees, and therefore, it represents a two-fold axis. And then the value of B prime A prime in such a situation turns out to be m value becomes 3. So, it is 3 times A B. Now, this defines a unit cell, because now we define our unit cell in terms of these periodically repeating patterns, and this periodically repeating pattern will now have to repeat in all 2 dimensions to generate the 2-dimensional lattice. So, the basic unit cell therefore can be defined as a quantity which has a direction A and a direction B in 2 dimensions, and the angle between them is not necessarily 90 degrees, it could be any angle. So, this therefore defines one possible type of conventional unit cell which we can have with a compound which is or a material which is displaying a two-fold rotation axis. Likewise, when the value of 1 minus n is minus of 1 and we have a cosine delta value of minus of half, the value of delta can be calculated, and therefore, n turns out to be 3. This is a 3-fold rotation axis, in which case the value of B prime A prime is 2 times A B, and the possible type of lattice which can be generated is A equals B, gamma is equal to 120 degrees. Now, I would like you to dwell upon the fact that when such a situation occurs, when we have a threefold rotation axis and then the B prime A prime turns out to be 2AB, in what way we are saying that the conventional unit mesh should be A equals B and gamma 120 degrees. This is something which I leave it to your imagination. The clue for this, finding out what it is left in the Escher's diagram which we saw earlier in the previous classes. Go to the Escher's diagram which showed the threefold axis symmetry. If you see the threefold axis symmetry, you will see that the unit cell which you can define in that situation will be something like A equals B, gamma is equal to 120 degrees. So, I want you to figure out likewise the case when the 1 minus m value becomes 0, the corresponding value of m times t, which is B prime A prime, will be AB, and this represents a fourfold rotation, and the lattice will be a square lattice. We have also given an example of this kind in the earlier class in the Escher's diagram. So, the idea is now that you have to go back and forth to the Escher's diagram and bring in the mathematical relation which we have derived here to see one-to-one correspondence. When the value of m is equal to 1, we get a six-fold rotation axis, and you see now AB is given as 0. I want you to find out why it turns out to be 0, and in which case A is equal to B and gamma is 120 degrees. It again defines a cell which is referred to later. We were going to talk about plane lattices. These now in fact define the plane lattices. These 1, 2, 3, 4 types of plane lattices we will get. In fact, we get a total of 5 plane lattices. We will discuss it when we bring in the discussion on different types of lattices that are possible in crystalline materials. At this juncture, we are now trying to tell you in this particular example of the slide that in this particular slide what we are illustrating is to show that the number of rotation axes that are possible are restricted to 1, 2, 3, 4 and 6 in crystalline objects which have the periodicity. And the same logic can be extended to 3 dimensions, and therefore, the rotation axes are 1, 2, 3, 4 and 6 only, and no other rotation axis is possible. This can be easily seen in a physical situation. Suppose you are given a 5-fold type tiles and you are asked to fill this entire floor of this room, you will see that it is not possible to do a closed packing. As we have been discussing earlier, all our diagrams in Escher's pictures are close packed. There is hardly any space that is left between them, and the close packing is a consequence which has to be built around periodicity. If we want periodicity, then we will have closed compact packing. If we do not want periodicity, we can have a 5-fold symmetry. That is how we have the so called 5-fold symmetry objects which are referred to as quasi crystals, which is of course an area of interest over the last few years, particularly since it got the Nobel Prize of 2013 or something like that. So, since the Nobel Prize was obtained, this particular aspect of 5-fold symmetry, the presence of 5-fold symmetry is actually also very important. But for conventional unit cells, which we are going to deal with in this particular course, we will restrict ourselves to close packed periodic objects, periodicity now driving the fact that there are only 5 types of rotation axes. So, even though our symmetry axis which we identified in the previous classes to be with respect to a point, with respect to an axis about which they rotate, and with respect to the planes about which they can reflect, the possibilities of types of such the symmetry elements get restricted to a point which will give us the so called center of inversion, the rotation axis which is 1, 2, 3, 4 and 6 only, and then of course the reflection across a mirror. So, this is as far as the periodicity issue is concerned. We will be introducing later on 2 other symmetry elements which go with this, that is the screw axis and the glide planes. I have already shown a Escher's picture in which this has been illustrated with respect to the glide plane, but we have just seen the picture and we have tried to see how the mirror followed by translation exists in order to preserve the periodicity. But I will introduce this 2-1 screw axis, and then the screw axis can be associated with the 3-fold axis, screw axis can be associated with 4-fold axis and also 6-fold axis. We shall see those independently later on as we go with our discussions. So, at this particular moment what we say is that in a 2-dimensional lattice the number of symmetry elements are restricted, and they are restricted to a point about which inversion can take place, a point in which we have a 2-fold rotation, 3-fold rotation, 4-fold rotation and 6-fold rotation, and then of course the last issue, which is a mirror plane. What is very important is when we talk and consider the issue of inversion symmetry, the inversion symmetry is not a 2-fold symmetry. It is not restricted to the 2-dimensional objects. 2-dimensional objects, whatever inversion we get will be the 2-fold axis rather than the inversion center, because the third dimension, the so called x bar minus x minus y minus z, brings in the issue of third dimension. So, what we are discussed here is only in 2 dimensions, and therefore, the presence of the inversion center in 2 dimensions does not exist. This must be borne in mind, and therefore, we will not see an inversion center in the diagrams which we have shown in the earlier Escher's diagrams. If we want to show the inversion center, which we showed with respect to a molecule in the earlier diagrams, we took the case of a iron diphenyl iron compound, in which case we saw that the center of symmetry indeed represents a 3-dimensional object rather than a 2-dimensional object. This is a take home lesson from this slide, that the center of symmetry will come into picture, the inversion center will come into picture only in 3-dimensional objects. If the object is purely 2-dimensional, it will not have the inversion center, and this is an issue which becomes extremely important when people are dealing with liquid crystalline material. When people deal with liquid crystalline material, there is order in 2 dimensions, but there is no order in the third dimension, even though there exists a third dimension. So, in such situations, there are different kinds of phases which come up as a consequence of liquid crystalline moieties, and this becomes an area of study which is of extreme importance in liquid crystals, particularly with the importance of liquid crystal displays, which have now become a common practice. It is a common household phenomenon. The liquid crystal screens which you see in the latest TVs and so on are essentially based on the symmetric objects, which are 2-dimensional in nature rather than 3-dimensional as far as the crystallinity is concerned. Right. So, having seen this particular slide, we will go and examine how we represent these symmetries. This is something which we saw quickly in the last class, but in this class we will go into the detail of how these representations are made, and this is the representation which is universally accepted, and it is the one which is followed by the International Union of Crystallography. In fact, the course which I am now giving is essentially considering the facts that there are certain rules and regulations which have been formed by the International Union of Crystallography, and that we must follow through the entire course. So, the way in which we represent, for example, a 1 bar symmetry, which is the symmetry where we invoke the inversion center, that is represented by a open circle. And you see that open circle does not exist in any one of these except at this position, which is the 3 prime position, and this 3 bar position has a center of symmetry which is inscribed inside the 3-fold symmetry. We will describe this in more detail when we talk in terms of the objects and how the objects get generated with respect to the various symmetries. But in general, you see the presence of center of symmetry is not invoked in any other B, C, D, E, which are explained in this about the various types of projection and the axes which we consider in this diagram. So, essentially 1 bar is shown by an open circle, a little open circle, because the bigger open circle would represent an object. We will see that in a few minutes. So, this is a small open circle which represents the center of symmetry or the inversion center. 2-fold, which is now coming out of this projection, out of this board, is essentially represented in this form, and then it is blackened inside to show that it is a full-fledged 2-fold rotation axis. That means there are certain relationships which have to be followed by the objects which are located in this space. Do not forget that once we define these symmetry elements, the symmetry elements are applying to the entire 2 or 3-dimensional lattice which we are going to take into account. So, therefore, every point in that space will be obeying the 2-dimensional 2-fold rotational axis. So, any point you put in that box will have the 2-fold operation validated. So, we will always have the 2-fold rotation axis being validated for every point in that space, whether it is 2-dimensional or 3-dimensional. Similarly, the 3-fold is rotated, notation is a triangle, and for 4-fold it is a square, for the 6-fold it is a hexagon, and so on. I have also illustrated here the so called screw axis, which we did not define as yet, but then we mentioned it as in the passing, and also there was an example which was given in the earlier slide, and later we will probably give it in your questionnaire to check out what is how you interpret these screw axis. Essentially, a 2-fold screw axis is one in which the object undergoes a 2-fold rotation followed by 1/2 the unit translation. So, if our unit cell is defined as A and B with respect to A and B, and if this 2-fold axis is with respect to A, let us say, then the 2-fold axis is now doing a rotation of 180 degrees from the position which is now representing the object. So, the object is here, it rotates by 180 degrees, it comes over there, and then it gets translated by half a unit. This translation of half the unit in fact is very important, because what it does now is to take that position which is now at half distance away from the plane of this board, of the illustrated board. It is half the distance away in terms of the unit cell dimension. So, suppose the unit cell dimension is, let us say, in that direction is some c, then it is half that of c. That means the translation component associated with this screw axis is 1/2, 1 divided by 2, and this now then goes through again the procedure. That means this now rotates again by 180 degrees. Translation is again half the unit, so that we get the translational periodicity restored. See, the question here is the understanding that is required in all these screw operations, which are shown here with all the symbols which we are going to employ in later classes, is essentially to tell you that the periodicity again plays a role in defining these screw axis. If there is no periodicity, there is no screw axis. If there is no periodicity, there are no what we call later as the glide planes, which are shown in this part of the illustration. So, effectively what it means is that the periodicity now is restored, but not within the one unit cell, but in the next unit cell, because there is no differentiation between one unit cell and the next unit cell because of the translational periodicity. So, whatever is there in the first unit cell repeats exactly the same in the second unit cell, the third unit cell, the fourth unit cell, and so on. And as a consequence, if the object is located in the plane here, then that particular object will repeat itself 1 unit away in a direction perpendicular to this board, and therefore, we will see that 2-1 screw axis is a valid symmetry element. Now, what do we mean by a valid symmetry element? This brings us to the issue of defining what are known as point groups. So, each one of them which are illustrated here defines what we would later realize and explain as point group symmetries, except that the translation components involved descriptions which we have here are not point group symmetries, because they are not keeping the point information intact. That means, if I take for example a 2-fold axis, the 2-fold axis will have an x, y, z, and then if the 2-fold axis is to the y axis, we will have a minus x, y, minus z. What you notice is, if you operate the 2-fold axis once again on x minus x, y minus z, you will get back x, y, z. And whenever we have these kind of operations, these operations of symmetry are referred to as point group symmetries. So, a 2-fold symmetry therefore represents an operation of on any point x, y, z in space, which can go over to minus x, y minus z, and that minus x, y minus z will now go to x, y, z. So, this is the relationship to represent a 2-fold symmetry axis. So, the 2-fold symmetry axis, which is representing this is represented by this symbol, will take any point x, y, z in space and take it to minus of x, y minus of z if it is a 3-dimensional space. And then we see that this particular 2-dimensional 2-fold symmetry operation can be repeated on minus x, y minus z to get back x, y, z. Now, such issues where we are going from x, y, z and operating the symmetry, coming back again operating the symmetry and coming back to x, y, z to the original position, This then defines what is called a point group, and we will see how many possible such positions can come in and how many such point group symmetries can come in. So, the property of the point group is that when we operate this symmetry more than once, depending upon how many such operations are allowed by the symmetry which is present here. For example, in the case of a two-fold axis, x y z goes to minus x y minus z, and this again when operated will come back to x y z. So, there are two positions which will be generated by a two-fold symmetry operation, and these two positions are also referred to as equivalent points. Equivalent points, they are equal to each other. So, there is no distinction between what is there at x y z and what is there at minus x y minus. So, therefore, they become the so called equivalent points. Regarding the issue with the screw axis which are shown here, the 2-1 screw, 3-1 screw and so on, there is always this translation component, this 1/2 which is associated with it. So, once we bring in the translation component, it is no longer in the within the point group operation. The point group operation will involve another translation of 1/2. So, since the translation of half is involved in case of a 2-1 screw axis, it will not be called a point group. So, what we have to do is the corresponding point group for 2-1 will be a two-fold, and therefore, we will have no additional point group coming due to these translational symmetries. The other issue which is shown down here is the issue associated with more than one symmetry operation. We will discuss this in more detail in the coming slide, but more than one symmetry operation would mean that we have, let us say, a two-fold symmetry, a two-fold operation, and on the two-fold operation we will also have an inversion center. That means, we now combine the three-fold rotation with inversion center. This, please note that this is not going to involve any translational component, and therefore, this by itself can be a point group. Let me repeat, since the operation of a three-fold and a four-fold, for example, let us take the four-fold, or let us take simply the two-fold rotation axis. The two-fold rotation axis now, if it is operated along with the presence of an inversion center, what happens is this x y z will go to minus x y minus z, that is by the two-fold operation. Suppose we also have an inversion center associated with it, then what happens is that the operation will now generate an inversion operation as well. So, effectively what one would leave finally is an operation which can become what is known as a mirror operation. So, in the case of a mirror operation, x y z will go to x minus y and z, and the x minus y z will come back to x y z, and that would be a mirror operation. So, that is why there is no 2 bar shown here in this part of the slide. We are showing the 3 bar, 4 bar and the 6 bar. The combination of a 4-fold symmetry along with a center inversion center therefore becomes an independent point group, because there is no translational component that is associated with it. Whenever there is a translation component associated with it, it is not a point group. So, therefore, all the translational point associated information, like in the screw axis as well as in the so called glide planes, which we will discuss more and more as we go along, these glide planes also will not be independent point groups. So, the point group therefore is defined in such a way that the symmetry operations are confined without the presence of translational components, even though the requirement of a point group is that we should have it in a translationally periodic system. The point group validity is there only if there is a translational periodicity in the system, but the translational periodicity that is present in the system is reflected not in terms of the generation of the so called equivalent points. So, when the equivalent points are generated, those equivalent points should be within the first unit cell. Whenever they are within the first unit cell, they are just operating on that particular point about which we have the axis, and therefore, there is no doubt in the mind that to call that as point group symmetry. But remember, point group symmetries which we are going to restrict in terms of 2-4 3, 6 rotation axes and so on, the point groups will be restricted to a total number of 32 as a consequence. So, before the next few classes we will know how these 32 point groups come in, and I think we will now end this particular class and then go to the next one.